Okay. Okay, let me quickly go through the outline of this chapter. First, I give an introduction to information retrieval, and then I will address some traditional techniques, like traditional information retrieval models, like the Boolean model and the vector models. Now the current trend is using vector models and use some generative like the LLM, large language models, to do the generative information retrieval. I will also address this topic. And finally, I will show how to evaluate your retrieval system's performance. Okay, there are some common used metrics and some benchmarks. Okay, so I hope you can understand what metrics we can use, and then when you read some related papers, okay, you will know how do they do their experiments. Okay, so let me skip because last week we already okay. So I want to address the cross-model retrieval for you. Okay, so last week we say there's a different way to do the information retrieval. Okay, a traditional ways. Okay, we give you a text, then I find a set of documents for you, like Google. Or you can use give an image, and I return you a set of images for you, like use Google Images. And the cross-model retrieval I think it's more powerful, because it's a closed modality. It means you can process the retrieval from different modalities. For example, you can give it with image as your query, and then the output will return you a set of a text document, like the ingredients or the instructions to tell you something, to tell you the recipe of this image, like this. So the recipe is in text modality, and your image this photo is the image, it's a visual modality. So they are from different modalities. But with the cross-model retrieval, we'll try to analyze the information from different modalities and try to generate a joint representation from both image and the text. Okay, so that you can do the retrieval. You can compute the similarity between the image and the text, like this. Okay, so it's called a cross-model retrieval. Okay, so here some examples show I give you a photo as a query image here, and the system, the cross-model retrieval system, will give you retrieve ingredients for this photo. Okay, you can compare with the correct answer because it's a true ground truth. And compare. Okay, they are very similar. Okay, and also you can also use query images to find its corresponding images from the database. Okay, so cross-model retrieval can retrieve, use image to retrieve text and also to retrieve images. So and then you can do it reverse. Okay, you can input a text as your query, and the retrieval result can be images or text. Okay, so it's a cross-model retrieval. And now is a current state-of-the-art to do the cross-model analysis, as called a clip. They try to connect in the text and the images. So you can consider it's also a cross-model analysis way. Okay, so this clip actually is this system is from this paper, Redfold. They are from the OpenAI. So they published this paper in It's called Learning Transferable Visual Models from Natural Language Supervision. It's published in an international conference on machine learning in 2021. So it's 4 years of course as papers, and now it's become you can think it's now becomes like a benchmark. So every new cross model analysis or retrieval models, they will compare with CLIP. And Chih-Yi is like a backbone, and then to do some modification or to develop new models and then compare with CLIP. Okay, the CLIP stands for the abbreviation of these terms, contrasted language image pre-training. So the abbreviation is CLIP from here. So the main idea here at least here is he tried to learn a visual concept from natural language supervision. Okay, so it collect plentiful abundant data from the internet. So they collect the images and the corresponding text. They pair together and to use this information and use these data pairs to do their training. And the idea they want to, the main issue they want to address is they hope they can build a system that can be applied to any visual classification. So like the image classification. Okay, so for this test, you can just simply provide the name of the visual categories and perform a zero-shot capability. Okay, so what is really want to do? Okay, you can see it's copied from the OpenAI's website here. Okay, so from these images, these figures, they show that, okay, so a traditional image classification test, we usually, for example, will choose a model, for example, like the ResNet. Okay, use the ResNet as your backbone, and then you choose image data set. Here we choose, for example, we choose the ImageNet. So ImageNet is a very popular data set. It's open and it contains 1,000 categories for you to do some image classification. Okay, so we use the ResNet and use the ImageNet they provide the training data and also the test data. Okay, we use the training data to train your models. Okay, we call it a pre-trained model by using the ImageNet. Okay, so if you use the ImageNet to train the model, and then here we try to apply this model on the following data sets. So first one is ImageNet. Okay, so you can see its performance is quite good. It's 76%. Okay, I think it looks good. Okay, but if we use this pre-trained model, okay, to test the data in the ImageNet, because they are from the same data set, so I think they can performs good. But if you use the pre-trained model to test in another data set, but you didn't use any training model, use any training data from the next data set called ImageNet V2. Now you can consider it's the second version of the ImageNet, but the training data and the test data are totally different from the original ImageNet. So you see, it's a set of image of banana. Here you see the banana in ImageNet, but in ImageNet V2, the banana's image are very different. Okay, you can see some green banana here, and some banana slice, and the banana juice. So they're very different from the original ImageNet. Okay, so if you use the pre-trained model from the ImageNet, okay, but now you want to perform like a image classification on a new different data set. What happened? Okay, because the image are somewhat different, right? So you can see its performance is degraded. Okay, degraded to 64%. Because of the pre-trained model, it didn't use any training images from the ImageNet V2. Okay, we didn't train again. Okay, so we just use it. I like to perform a zero shot. Okay, to do the classification and the performance degraded. And then for the other data set like the ImageNet predictions, okay, you can see the images are they contain some images like cute and human-like bananas. It's a very like a cartoon style. So it's much different compared with the ImageNet training data. So you can see the performance is getting lower. So you can check others like the ObjectNet is another data set, ImageNet Sketch, or the ImageNet adversarial. You can see the performance are not very good. Yeah, because the pre-trained model, they only train the model on ImageNet dataset, but not train using the other dataset training data. So its performance is not good. Okay, any problems? Alright, so but how about clip? You can see the left column. The clip, they collect the data, the training data from the World Wide Web. So they don't use any training data from ImageNet or the series. They don't use any the training data from this. They collect the data by themselves from the World Wide Web. Okay, they use the vision transformer as their backbone and train their data, their self data from the World Wide Web, and to perform the zero shot classification like this. So when the clip is performed to test their image classification on ImageNet, okay, they can achieve a quite good performance. Is comparable with the ResNet that using ImageNet to do the training. But nonetheless, the clip don't use the training data from ImageNet. Okay, but they use the World Wide Web data. They collect it by themselves, but it's a more big training data set. Okay. And how about the other data set? You see, for ImageNet V2 and the other data set, it still performs very good, even for such a very special ImageNet Sketch data set. Okay, so they can still perform 60% accurate. Okay, remember it's zero shot. They don't use any image data, training data from this data set, but they still can perform a very good result. So this means the pre-trained data of a clip is very powerful. Actually, you don't need to train. You can directly just use the pre-trained model and to apply to deploy into your applications to perform a zero shot. Okay, so if you can get the training data, okay, you can fine tune the pre-trained model. I believe their performance can be improved. Okay, but even you don't perform any fine-tune process, they can still achieve a very good result like a zero shot. Okay, any problems? Okay, so this system is a framework. Okay, it's from their paper. Okay, OpenAI's paper. Okay, you can see the summary of their approach. Okay, so first, is perform the training. It's called a contrastive pre-training. Okay, in contrastive pre-training here, okay, we collect a large amount of your training data, and we collect the image and the corresponding text description here. Okay, you can see it's compare the OC pub to describe this dog image. Okay, so each of them for the text, let's throw the text encoder. Okay, they will train a text encoder here to generate the embedding from the first text, the first document, second document. And for image, they throw put it into the image encoder to generate the embedding. Okay, for the first image, second image, to the nth image. And note that remember that the first document is paired with your first image. They are paired. Okay. Okay, so you have a set of text embedding and a set of image embedding. Then you can perform to generate a matrix as by applying the inner product between them. Okay, so here, this one is the inner product with the first text and the first image. Okay, so you can compute the inner product and also compute all the inner product to form a matrix like this. Okay, and then we can perform, based on this matrix, we can perform a contrastive learning here. Okay, here the contrastive learning is a self-supervised learning. So this means you don't need to provide any category information. You don't need to use the label. Okay, you just use their use their pairwise information to do the training. Okay, so here you can see consider this image 1. Okay, so given you the image 1, okay, I can compute all the inner product with other text, right? And you can treat it as a classification problem. Okay, so because they are inner product, you can consider they are the similarity. They reflect the similarity between the image and all the text. Okay, so you can think it's a score. It's a score means the score, the relevant score for the T1 to I1, and the next is the relevant score for the T2, and the third is the relevant score for the T3 to the I1. Okay, so you can think it's scores, the relevant score to image 1. Okay, so the higher means they are more relevant. Okay, so and then because we can treat it as a classification problem. So because I1 is paired with T1, so it means this score should be highest. Consider this row. This one has a highest score here. Okay, so you can treat this as a classification that the correct answer will be the first category for image 1. And the others are incorrect. Okay, so you can set, you remember the cross entropy? In cross entropies, you give a set of probabilities here, but only once. It's a 1/2. You remember it's a 1/2 label. So only this category has a label 1. Others should be 0. It's your ground truth. And here is your prediction scores. So you can perform the cross entropy to compute the loss. Okay, so it's for the image, the first image. So it's like you can calculate the classification loss using the cross entropy to calculate the loss for image 1, and then you will repeat the same process to do image 2. Okay, for this the second row, you compute the similarity scores, and only the second category are correct. Okay, so you can perform to calculate the cross entropy, and for third until n. Okay, any problems? And you can do it again for consider the text document. Okay, so for the first document, you can think all its relevant scores to the nth images is in the first column, but only this one is correct. So we can do a similar way again. So do a classification, only this one is correct, others are 0, should be 0. Okay, to calculate the cross entropy. And it's for the text 1, okay, and for text 2. Okay, you can calculate in total and cross entropy loss here. Okay, then you just sum all this together and to do your training. Okay, any problems? Okay, so it's the first step for your picture model. And the second, okay, for the second, so we can create a data set. It's a new data set, for example, like the ImageNet, Sketch, or any other new data set. It has the following categories like a plane, car, dog, bird. Okay, you have the following categories. You just insert it into a text description, a document here. So you say as a photo of any object from here. For example, like a photo of a plane. Okay, you can use the first categories, insert into its text. Then use this text, throw your pre-trained text encoder. Train from here. Okay, use the text encoder to generate your text one embedding, and generate all the categories embedding for the new database. Okay. And the final is to perform the zero-shot prediction. The zero-shot predictions give you any images from the new data set here, and we use the image encoder, also train from here. And then is the image embedding. You can compute with the categories embeddings, and you will get the inner product is the relevant scores. You just pick the highest one. For example, this here. We show that their scores, their inner product is highest. So I pick this one represents a photo of a dog. So it means this image should be classified into the dog category. So the whole process is a zero shot. Okay, any problems? Okay, so I think Clip provide a very astonishing, a very impressive way to connecting the text and the image information. But to do this, to generate such a very powerful model, you must have you must be very rich to have a very good equipment to train, to collect a lot of data and to train. So maybe several months by using maybe 1,000 NVIDIA, the high-end card, display card to do the training. So, but I think OpenAI is also very generous. So they release this train model. Okay, so that we can just use it, download it, the pre-trained model, and we can use it to fine-tune it, okay, for our deploy to our applications. Okay, so it's the clip system. I hope you can know it now. Can treat is a benchmark for the cross model retrieval and analysis. Okay, so it's recommended system. We have mentioned it last week. Alright, so it's the basic text IR system architecture. It's what I call the traditional information retrieval system, like this. So let's me copy it again. Okay, the first here you see the left-hand side is your user test. Okay, so give you a query, and I will transform your query to a representation. Okay, or call embedding as a text embedding here. And the right column shows document view. You have a set of documents in your database, and each document you also transform it into document representations. Okay, that should be the document representation and the query representation should be in the same embedding space. Or they should be represented in a vector form. Okay, and with the same dimensionality. Okay, so that they can perform the similarity comparison. We usually calculate by using the Euclidean distance or the inner product to calculate the relevance between the query and the documents. Here is the index structure here. So all the documents, because the number of documents are very large, so if we want to build a very efficient search system, we should use an index structure. Okay, we will talk about in our data course. So to tell you some very efficient and very accurate index structures can be used to accelerate your search process. Okay, so we can generate, compute their similarity and to do a ranking. Okay, and we can retrieve the top 10 documents for the users. Okay, so it's a traditional text IR system architecture. Okay, but now we will have it's a new generation for generative information retrieval because of the rapid development of the large language models. Okay, so it's called LLM. So now your IR retrieval system now should be used generative way to complete the information retrieval task. So here I highlight two directions. Okay, first is the generative retrieval, and the second is the response generation. Okay, this figure is from the paper. It's called a formation to generation. It's a survey paper published on the archive last year. Okay, so this figure shows that we can discuss the information retrieval according to the categories. The first one, the traditional retrieval. Okay, the traditional retrieval is like this. It's just the same as this one. Okay, so our traditional IR system. So here in their paper, they say, okay, the traditional retrieval is like this. So it will query how to cook a steak. Okay, and throw the encoder, and try to transform it into a text embedding, a text representation. And here is your index, database index that you can perform the similarity matching. Okay, it's the same as the previous slides. Okay, so here is the result. You can see given a query here, I can retrieve top 3, the top 3 highest ranking documents for the user. And but now if we use the generative retrieval, okay, so how can we do it? Okay, it's okay. We give a query here. It's a text query, and through the language model, and the language model will base on a document ID prefix system to generate a constraint generation. So it means the language model give a language model the input as a text description here as an input. Then the language model will output a document ID for you directly. It doesn't perform any similarity matching here. No, it just generates the document ID to you. So you generate the top 3 document IDs. So you just retrieve from your data set. Okay, so basically for the traditional retrieval and the generative retrieval, they can, for the user, they don't know what's the insight in their system. Okay, the user just see, okay, the result. I can get the result. The results are the same. Yeah, but inside their system, they use a different way to perform the retrieval. And the next one is called a response generation. You try to directly provide the information you want. Okay, so give you a question here. Okay, so the language model will train by using some training strategy to train a model. Okay, so next, when you give the query, the language model will give you the answer like this. It's not no more a list of documents. It just give you, according to your questions, I will give you like a conversation with the user. I give you the ingredients and equipment and also the instructions. Okay, like a chatbot to give you answers. Okay, so here I give you some formal, general definition for this technique. Okay, given a document collection E and a user query Q and information retrieval, our goal is to calculate the relevance scope between the document and each document and the given query Q. And for the traditional information retrieval, here, how to calculate the relevance scope? Okay, you can see here we use, here is an example, we use the TF-IDF. We will talk about how to calculate it later in today's course. Okay, TF-IDF is, you can see is try to calculate, to reflect the importance of the term for the in the given document. Okay, so here the term means a common term appeared in the query and in the document. Okay, so we just summarize all the terms, the TF-IDF in the document and the time with the TF-IDF in the query. Okay, so very simple equation to express how to calculate the relevance scope between the query and the document. Okay. So any problems? I will detail it later. And for the generative retrieval, how to calculate the relevance between between the given query and each document. Here we can formulate it as a conditional probability like this. So the goal is to generate a document ID called B prime. So the ID may be different from it's a new ID. Okay, we will have the ID will be different from the original dataset ID. Okay, so we will calculate the probability. When you given a query and your model, we calculate the probability to generate D prompt. How to calculate D prompt? Actually, it works like in a generative way. You can see like auto-regression questions. So you can see here Suppose we are going to generate T tokens as your document ID, and for each token we will use this form. It means auto regression. Auto regression means if I want to generate the ith token, I will use the I-1 token as the information. Okay, so if you want to generate the second token, you have to use the first token to generate it. Okay, it's called auto regression. Okay, so just ties all the probability together, the conditional probability together. Okay, you can find, you can use it to calculate the probability for the document ID prompt. And for the next one, for the large language models, it's like the GPT or Llama. Okay, so generally it follows encoder, decoder, or the decoder-only framework. Okay, later we will, in today's course, we will talk about a little bit about the transformers and to details the architecture of encoder and the decoder. Okay, so next, let me give you a concept about the traditional retrieval model. I will just talk about the Boolean model and the vector models for you. Okay, let's take a break of the video recording.